Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have the lecture slides, you may refer to my GitHub page at this given link. In last lecture, we were discussing Fisher discriminant analysis that was applicable only for two class problem, but in this lecture we will discuss multiple discriminant analysis, that is the extension of Fisher's linear discriminant analysis for C class problem. So multiple discriminant analysis involves C-1 discriminant functions for C class problem, and the reason behind is that the between class scatter matrix is computed using outer product that we have seen in previous lectures, and the rank of that between class scatter matrix is at most C-1 in case of multiple discriminant analysis. So here we are seeking for projection of the data sample from D dimensional feature space to a C-1 dimensional feature space where D is greater than equal to C, that is assumed. Okay. So using the same concept that we have considered in Fisher linear discriminant analysis, we can define the criteria function for multiple discriminant analysis where we need to maximize the ratio of between class scatter matrix and within class scatter matrix. So in this problem we need to find the rectangular matrix such that this criteria function is to be maximized. So we have to maximize this criteria function for a particular value of this rectangular matrix W. Now look at this plot. Here three dimensional distributions are projected onto two dimensional subspace, that is described by the two normal vectors W1 and W2. Informally we can say that the multiple discriminant method seeks the optimum such subspace, that is the one with greatest separation of the projection. So when you will look at this, then here we have the greatest separation among these distribution in this two dimensional space. But on the other hand, in the two dimensional space which is denoted by a normal vector W2, here the separation between the class is not good enough, so that we will get the good accuracy using certain classifier. Let us optimize the criteria function for the optimum value of the weight vector W. So we have the criteria function as JW equal to between class scatter divided by within class scatter, and that is defined by this expression. Okay, where SB is SW is within class scatter matrix. Okay. So how to compute these matrices for C class problem? Here the calculation of SW is very obvious, that we can write SW which is the within class scatter. So we have to take the sum of all individual class scatter. So we can write something like this. Okay. So now we can write in this form where I equal to 1 to C, where C is the number of class. So summation of all the scatter matrices corresponding to So different classes where Si can be defined as summation x minus mi x minus mi transpose, where x is the set of samples from set I or ith class, and mi, which is the mean of the ith class sample, is 1 by ni. Ni is the number of samples in set di. Okay. Here di is set of data samples in ith class, and ni is the number of data samples in ith class. Okay. Unlike Fisher's discriminant analysis, the proper generalization of SB is not quite so obvious. So what we have to do, suppose we have total mean vector equal to m, that means whatever the total number of samples. So we have total n number of samples, so we will take the total mean. So here, so this summation can be split into two summation, where first summation index will show the class index, and the second summation will show the number of samples in individual class. Okay. And here this term is nothing but the summation of all the samples in the ith set, ith class. So that can be written as the number of samples in the ith class into mean of the ith class. So we can write the total mean m equal to 1 by n okay. Now we have to find the total scatter matrix. Which is defined as St equal to summation of x minus total mean x minus total mean transpose for all set of samples. So here we have total scatter matrix is defined by this expression. So here again we can split this summation and rewrite the expression as okay. So we can write in this way. So if you will see this expression, this is basically the within class scatter, okay, because this internal term is basically the scatter matrix of individual class, and we are taking sum of all the scatter matrix summation over all the classes. So this is within class scatter matrix plus the rest of the term can be defined as So, here Ni comes because this in this term there is no component of x in this expression. So, we can replace with the number of samples in each class. Fine. So, we have the total scatter matrix equal to ST equal to SW plus SP. Where SB equal to this much. Okay. So, here in multiple discriminant analysis, projection from d-dimensional space to a c-1 dimensional space, which is accomplished by c-1 discriminant function. Functions. Okay. So, what we can write? We can write y I equal to w I transpose x. So, here y is basically the small italic notation and w is basically a vector which is small upright vector. So, here I equal to 1 to c minus 1 because we have c minus 1 discriminant functions. So, this expression we can write in the matrix form. Let us write first okay. Where yi can be viewed as the component of vector y and weight vector wi are viewed as the column of matrix W. So, let us check the dimensionality of these vectors and matrices. So, this y vector having the dimension c minus 1 into 1 and this matrix W having the dimension D cross C minus 1, where D is the dimensionality of the feature vector and this is x. So, this is x basically. So, here x1, x2 and xd are the D components of the feature vector x. So, it has the dimension D cross 1. So, here this is basically the transpose. So, that this will become C minus 1 by D dimensional feature vector. So, this and this will be multiplied. So, it will satisfy the dimensionality multiplication. Now, we will try to find the scatter matrices of the projected samples. Okay. So, for that let us consider x1, x2 and xn are n number of data samples and their corresponding projected samples. We can write y vector y1, y2 and yn. Okay. So these are basically the projected samples. Okay. So we can write mi, where mi tilde is the mean of projected samples from ith class. So that is basically 1 by ni and summation of projected samples, where projected samples belongs to ith class. Now we can compute the total mean vector of projected samples. So this is the m tilde, and we can write 1 by n is the total number of samples, and similar expression that we computed earlier. Okay. Also we can define the within class scatter matrix of projected samples. Okay. So SW tilde equal to, so we can write like this, okay. So similarly we can write the between classes scatter matrix that we derived earlier. So what will be the between class scatter matrix? SB tilde equal to summation over all the classes okay. So till now what we derived? SB, okay, and SW, then SB tilde, SW tilde, okay. So it is very straightforward to show that SW tilde equal to W transpose SW. So here this W is capital W, where W is basically a matrix, and SB tilde equal to W transpose SB W. Okay. So these equations show that how within class and between classes scatter matrices are transformed by the projection of the lower dimensional space. Okay. Now how we can derive this relation? It's very obvious. So let us derive this. We know that SW tilde equal to okay. So we can put y equal to W transpose X, okay, and Mi tilde equal to W transpose Mi, okay. So put this one, so it will become W transpose X minus W transpose Mi into W transpose X minus W transpose Mi transpose. Okay, so now here we have X, where X is the set of samples from set Di, where X is the set of samples from Di. Now we can take out the terms which can be taken common. So W transpose X minus Mi, X minus Mi transpose W, okay. So now we can write W transpose summation I equal to 1 to C, and X is the set of samples from set, X is the samples from set Di, X minus Mi okay, and this is nothing but that we already derived within class scatter matrix. So we can write SW tilde equal to W transpose SW W, okay. Fine. Similarly, we can derive the other relation as well. As we know, SB tilde equal to summation Ni Mi tilde minus M tilde Mi tilde minus M tilde transpose, where I is from 1 to C. So just put the value as Mi tilde is nothing but the W transpose Mi, and M tilde equal to W transpose M. Okay, so just put in this expression, we will obtain Ni W transpose Mi minus W transpose M, W transpose Mi W transpose M, okay. So here I equal to 1 to C. So now take the common W transpose and W from both sides. So W transpose Ni Mi minus M, Mi minus M transpose W. So now look at this term, this is nothing but the between class scatter matrix. So SB tilde equal to W transpose SBW, okay. So we derived these two terms. Now look at the solution of our criteria function. So what was the criteria function? we had JW equal to SB tilde divided by SW tilde. Okay. Okay. So we have to maximize it for an optimum value of W. So as we did the solution in case of Fisher linear discriminant analysis, so same solution we can do here as well. So the columns of an optimal W are generated eigenvectors that corresponds to the largest eigenvalues, and that can be obtained as okay. So what we can write as B minus lambda I is W I. Okay, so this is the solution. So if SW is non-singular, so if this SW is non-singular means what? The determinant of SW is not equal to 0, then this expression can be converted to a conventional eigenvalue problem. So let us see how we can convert it. SB Wi minus lambda I SW Wi, just we are expressing the term, and then we can write SB Wi equal to lambda I SW Wi, then multiply both side with SW inverse. Okay. So now look at this term. This expression is quite familiar. So here this is our matrix where lambda I is the eigenvalue and corresponding eigenvector is Wi. So we need to solve it. So the computation of the SW inverse is basically very expensive. So what we do, instead of solving the eigenvalue problem, we solve the characteristic polynomial which is given by SB minus lambda I SW, which is derived from the previous expression. Okay. So here we can solve this expression, and after solving this expression, we can obtain the eigen values. Okay. So when we have the eigenvalues, then corresponding eigenvector can be calculated, and how we will calculate? We have to solve the expression SB minus lambda I SW Wi equal to 0 for Wi calculation. So here this is our solution. So we will have the vector for C minus 1 discriminant function. So that will give you the complete picture of the transformation matrix, so that our the data samples in the lower dimensional space will have the best separability. So this was the multiple discriminant analysis. So if you have any doubt, you can ask in the comment sections. Thank you.